Another paper too from November 22. Starting off with percentage by mass calculation. In this case, for a compound called ammonium nitrate that contains 2 nitrogens, we will want to count the mass of the 2 nitrogens first and divide that by the overall molar mass of the compound. So let's start with 2 nitrogen relative atomic mass, which is 14.01. Be aware, you can't just use 14, but the exact 14.01 value as quoted in the periodic table. We'll divide this by what? The overall molar mass, which would be the 2 nitrogen plus 4 hydrogens plus the 3 oxygens. If we do the math, we will be dividing 80.06 we'll be dividing 28.02 by 80.06, which would be 35%. Next up, we know ammonium ion NH4 plus would be a bronzed acid because of its potential to donate a proton to become an ammonia. Because donate proton. Nitrate NO3 minus has quite a tricky Lewis structure, but we'll start with the central nitrogen that is bonded to 1 oxygen using a double bond. One of the 3 oxygens will be lucky to have the double bond, while the other 2 will have to opt to having 1 minus charge each, because nitrogen cannot supply any additional double bonds, which means there needs to be extra electron on the oxygens, so that in contrast to the usual 6 valence electrons, there are 7. Hence the negative charge. The central nitrogen has 4 electrons only compared to the usual 5 valence electrons, therefore will have a positive charge as well. And yes, each of the negatively charged oxygens will have 3 lone pairs. Ammonium nitrate has a pH, and we're going to find that pH because we're given the H plus concentration value right here. H plus concentration is a specific value, which means that we can put that value into the equation. pH equals minus log the H plus concentration. Do the math, and we will be given pH equals to 4.97. We now move to the next question, where ammonium nitrate seems to work as like a coolant in a way similar to an ice pack, except that we activate the ammonium nitrate ice pack, which is separated from water, and once it becomes dissolved in water, we're going to have the cooling effect. And why is that? It's because the ammonium nitrate dissolving in water is an endothermic process, absorbs heat from the surroundings to the extent where the temperature drops from 25.2 to 0.8. So the degree by which energy is absorbed will be measured by Q equals mc delta T, where mass would equal to the mass of water, 25.32 grams, times specific heat capacity, grams, joules per grams per Kelvin, times the temperature difference, which is 24.4. Going to swap the unit to Kelvin. Do the math, and we can cancel out the units to work out our final calculation value in joules, which is 2580 joules. That's the amount of energy absorbed. Not released, absorbed, therefore plus value by ammonium nitrate dissolving in water. So we have produced 2580 joules, we have absorbed 2580 joules of energy from the surroundings, and we want to know exactly how much ammonium nitrate has been absorbing this amount of energy. When we know that every mole of 1 mole of ammonium nitrate absorbs 25.69 kilojoules per mole. So what are we going to do? We're going to set up the equation that delta H equals to Q divided by N, where Q is the energy absorbed by ammonium nitrate, N is the amount of ammonium nitrate, meaning that N equals to Q over delta H, where Q 2580 joules divided by 25.69 kilojoules. But let's convert this to 25.690 joules per mole so that we can cancel out joules and have N equals to roughly 0.1 mole. And we know the molar mass of ammonium nitrate to be 80.06 grams per mole. Therefore, N times molar mass equals the mass, meaning 0.1 mole times 80.06 grams per mole equals to 8.01 grams, which is the mass of ammonium nitrate used to absorb 2580 joules. Apparently, the mass of water wasn't accurate. It had some degree of uncertainty, defined as 0.01 grams, as well as the temperature, 0.2 degrees Celsius, which means that the value we derived will also have degrees of uncertainty. We derived the mass of ammonium nitrate used to be 8.01 grams, which is inaccurate. And we have to find the degree of inaccuracy. How? How did we find the mass of ammonium nitrate? We worked out mass of ammonium nitrate by working out the Q, which was mc delta T over delta H. And then we divided this also by the molar mass, molar mass of ammonium nitrate. That's what we did, which means that we need to associate each of the factors multiplied, divided. We have to associate each factor with their uncertainties, percentage uncertainties, to which we already know mass has 0.01 grams over 25. How much mass of water did we use? 25.32. 25.32 grams percentage uncertainty. That's the percentage uncertainty for mass. We can ignore the specific heat capacity, right? Because specific heat capacity does not have any inaccuracy. Delta T does have inaccuracy. We need to count for 0.2. We're going to multiply that by 2 because we've taken 2 readings, right? The initial temperature and the end temperature, for which overall, there can be maximum of 0.4 degrees Celsius inaccuracy over the actual temperature delta T value we've used, which is 24.4. We can also ignore delta H because delta H value was given in the data booklet, so quite accurate. And we can ignore the molar mass inaccuracy as well. It's quite accurate. So we're going to sum the two percentage uncertainties, which, if we do the math, work out to be 2% for delta T and 0.04% for mass. Therefore, overall percentage uncertainty of ammonium nitrate mass is 2.04%, which means we can represent the mass of ammonium nitrate as 8.01 grams plus minus 8.01 multiplied by 2.04%, which would be 0.16344. But yeah, it's a long decimal number, and we're going to simplify it. And let's note how we've used one significant figure for both uncertainties, for mass and delta T. So we're also going to use one decimal place, which means we will convert the value to 0.2%. No, not percent, 0.2 grams. Plus minus 0.2 grams, absolute uncertainties. Unfortunately, the value we have calculated as 8.01 grams doesn't seem to be the actual value, the theoretical value. There is a discrepancy between the actual and the theoretical, and we're going to find the percentage error value, which can be calculated by theoretical, which is 9.5, take away the actual, the experimental, divided by theoretical. Now this is 9.5, take away 8.01 over 9.5, which would give us a value, and that value is 15.7%. Ammonium nitrate can be applied to decomposition, where dinitrogen monoxide, that's N2O, and H2O can be formed. Let's try and balance this equation, where N2O will be produced as well as H2O will be produced. Solid ammonium nitrate will be producing gaseous dinitrogen oxide and liquid water. To make sure there are equal number of nitrogens, oxygens, and hydrogens, we're going to have 2 H2Os produced for every 1 ammonium nitrate, which will also produce 1 N2O. The equation we have is completely balanced. Great. Next up is, given the amount, 5 grams of ammonium nitrate, we know the molar mass, therefore we'll know the amount in moles. We will know the amount of dinitrogen monoxide produced, because the amount of ammonium nitrate equals to the amount of dinitrogen oxide. We can use the molar volume of gas to work out the volume of dinitrogen monoxide produced. Now, 5 grams over 80.06 grams per mole is the amount. And we know that 1 mole of any gas occupies 22.7 dm cube. So we're going to multiply, or we're going to use the express the equation N equals volume of any gas divided by 22.7 dm cube per mole, where we know the amount N, we will say the volume equals to 5 over 80.06 times 22.7, which would give us the value of 1.42 dm cube. The delta H of decomposition can also be calculated with delta HF values using Hess cycle. For that, we will draw the Hess cycle first as follow. NH4NO3 solid becomes N2O gas and 2H2O liquid. This reaction has delta H value. We will be forming 1 mole of solid ammonium nitrate from nitrogen gas, hydrogen gas, and oxygen gas, which will have a delta H associated with it. And we call this what? Delta H enthalpy change of formation, the value being -366. Dinitrogen oxide also has this delta HF value, and that is specified as +82. Okay, so formation of ammonium nitrate releases energy, while formation of dinitrogen oxide absorbs energy. What about water? We don't have that information, for which we're going to look up the data booklet, going to section 12, we'll figure out what water delta HF value is, which we have found to be -285.8. 285.8. So what we know is that delta H equals to -366 plus 82 plus -285.8 times 2. We have to make sure we multiply -285.8 by 2 because 2 water moles are produced from 1 mole of ammonium nitrate decomposition. The delta HF is defined as the enthalpy change when 1 mole is produced. 1 mole of a substance is produced. So if we want to produce 2 moles of water, we'll have to multiply delta HF value of water by 2. Do the math, and we will be given the delta H value as -124 kilojoules per mole. Dinitrogen oxide will have a low structure. We can assume that to be quite difficult. We don't see dinitrogen often, but if we give this an attempt, we can expect there to be the central nitrogen that is covalently bonded to a single negative oxygen, where the single negative oxygen will have 7 valence electrons. Sorry, it will have 7 electrons compared in contrast to its usual 6 valence electrons, therefore given the -1 negative charge. Nitrogen, the second nitrogen will require a triple bond to satisfy full octet, where the second nitrogen will have a lone pair, which means that the central nitrogen will be positively charged. Why is that? Usually there will be 5 valence electrons, but the central nitrogen only has 4 electrons of its own. to have one single covalent and three single covalents in a triple bond. Now this is a linear structure. The molecular geometry is linear, as well as the electron domain geometry, because both electron domains are bonding pairs. Now, we can represent the Lewis structure in an alternate form, which can be derived by movement, delocalization of electrons, so that we end up with double bonded oxygen and nitrogen and double bonded nitrogens, where we will have negatively charged nitrogen because it has 6 electrons in contrast to its usual 5 valence electrons, and the central nitrogen remains positively charged, 4 electrons in contrast to its usual 5 valence electrons. We have a complex looking organic molecule we call chloroquine that apparently treats malaria. Don't need to know how the molecule treats malaria, but we should be able to identify how there are 2 benzene rings where 1 nitrogen substituted a carbon. There's a chlorine atom that has substituted a hydrogen of benzene, and there's a hydrocarbon with nitrogens inside. We're going to identify the secondary amino group in chloroquine as this NH group. This NH group is secondary because there are 2 alkyl groups and 1 hydrogen. There is a tertiary amino group which we don't need to highlight, but we can just acknowledge that N1 is bonded to 3 alkyl groups and therefore a tertiary. Okay. For those of you who are wondering what this amino group would be, well, it's got only 2 alkyl groups, but it has 0 hydrogen. Therefore, there's no room for reduction. There's no room for oxidation, and it cannot be oxidized, so it would be appropriate to refer to this as tertiary, that cannot be oxidized. Index of hydrogen deficiency is about counting the number of hydrogen H2 pairs that can be added to reduce unsaturated carbon, hydrocarbon compound, for which we'll count how many double bonds there are, triple bonds there are, and cyclic structures there are. It would be useful to convert the benzene rings to calculus structure to have double bonds specified as follow, out of which we can tell how there's 5 double bonds, 0 triple bonds, and 2 cyclic structures. So overall, 7 pairs of hydrogen, 7 H2 molecules can be used to reduce the structure there. 7. We're going to compare the length of carbon nitrogen 1 and the carbon nitrogen in the benzene ring. Well, the carbon nitrogen in the benzene ring has a bond order of 1.5 compared to bond order of 1 in CN1. And that's because we have partial double bond within the benzene ring, isn't it? So carbon nitrogen bond in the ring is shorter because partially double bonded with order of 1.5. This contrast with, in contrast to, single covalent bond that's order of 1 for carbon, nitrogen 1. Well, we know nitrogen is going to be more electronegative than carbon because firstly it's smaller, and secondly it has greater effective nuclear charge. Nitrogen is more electronegative because smaller atomic radius and greater effective nuclear charge. Allows nitrogen to be able to attract the shared pair of electrons stronger to itself. Chloroquine must have been synthesized from a precursor molecule, which there are two. One, 4,7-dichloroquinoline. Okay, quite a complicated name. We're going to disregard that. But we know there has to be another molecule that corresponds to the highlighted part. The structure will simply be as follow, except that instead of NH, there should be NH2. There should be one extra hydrogen that would have been lost in the electrophilic substitution for the initially existing chlorine. So let's make sure we draw not NH but NH2. Copper as a transition metal can be used as a catalyst, and the electronic configuration for copper is going to be Ar 4s1 3d9. Sorry, 3d10. It's not going to be 4s2 3d9, but 4s1 3d10 with one electron moved from 4s orbital in order to complete the 3d orbital, which would bring stability to copper. I've used the condensed electronic configuration, but you may also write the full electronic configuration starting from 1s2. When comparing the Maxwell-Boltzmann distribution of catalyzed versus uncatalyzed, we'll have the same curve, but the activation energy will be different for both catalyzed and uncatalyzed. So we'll draw the activation energy for uncatalyzed first and draw another for the catalyzed. EA catalyzed. The proportion of particles, reactant particles that successfully react without catalyst is the shaded area under the curve, which is smaller than the fraction of reactant particles that successfully react with catalyst. So we can write how the effect of catalyst is to lower the activation energy and increase the proportion of reactant molecules with energy greater than the activation energy to increase reaction rate. That's the purpose of any catalyst. We have a displacement reaction between copper 2+ and iron. The more reactive iron will displace copper 2+ from its solution. And we'll start off with the electronic configuration of iron 2+, which can be represented as AR. We'll start with the full electronic configuration of an iron atom, 3d6. Now that's the electronic configuration of iron, from which we will remove the 2 electrons in 4s. Therefore, AR 3d6 would be configuration for Fe2+. Copper has a mass defined by 63.62. The relative atomic mass is calculated from how there are 2 or more isotopes, in our case 65 mass isotope and 63 mass isotope, that both have relative abundances, and we'll need to account for those relative abundances to work out the relative atomic mass. That will be halfway between 63 and 65, but probably more skewed towards the 63 value because there are more of the 63 mass isotope. The percentage abundance of 65 is 31%, which compares with the 69% abundance of 63. So what we can tell is RAM of copper, which is 63.62, equals to 69 times 63 over 100 plus 31 times 65 over 100. Back to the displacement reaction of copper and iron. Iron is more reactive, will be oxidized, therefore will occupy the anode, so that we have the iron metal electrode in the anode, as well as Fe2+ salt solution in the electrolyte of the anode. Copper metal electrode will be in the cathode, as well as copper 2+. We also need to label the direction of the electron flow, which would always be from the anode to the cathode. What's the easy way to remember the electron flow? At the anode, oxidation takes place, meaning that lots and lots of electrons will be released. There will be a buildup of electrons, negative charge, around the anode, which contrasts with all the electrons at the cathode being taken up by the copper 2+ for reduction. The concentration gradient from high to low means electrons will flow from anode to cathode. Easy question, half equation for oxidation would be Fe solid becoming Fe2+ aqueous, releasing 2 electrons. Yes, we have a salt bridge where the identity is potassium nitrate. So salt bridge is a tube that contains potassium nitrate solution, where potassium plus would be separated to the nitrate anions and will be migrating to anode and cathode for the purpose of maintaining the charge balance of each half cell electrolytes. Maintain charge balance of each half cell electrolytes. That's the function of salt bridge. We know that in the anode, we will be producing lots and lots of cations. In the particular case of iron copper displacement, iron 2 plus buildup needs to be neutralized, will be balanced by incoming anions, which means that nitrate anion migrates to anode. This contrasts with the cathode, where we're losing lots and lots of copper 2 plus in the reduction to copper solid, which deposits to metal layer around the metal electrode. We need to maintain the positive charge within the cathode electrolyte, meaning that potassium plus migrates to cathode. Another organic reaction where we are reacting what seems to be an alcohol with a double bond with carboxylic acid to produce an ester. Alcohol plus carboxylic acid will produce an ester, and we need to condense water out, where we'll take out H2O and combine the oxygen from alcohol with the central carbon of the carboxylic acid, which if we draw out will look along the line of the following. This would be the ester, where the ester group, the functional group ester, is defined by COO, 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 that is bonded to two R groups. The empirical formula can be first calculated. The empirical formula can be calculated by first working out the molecular formula and seeing if we can make smallest whole number ratio out of it. So how many carbons, hydrogens, and oxygen are there? We see 1, 2, 3, 4, 5, 6 carbons. Carbon 6. Hydrogens 3, 5, 6, 7, 8, 9, 10. 10 hydrogens. Oxygen 2. Yes, we can divide the molecular formula by 2 to give C3H5O, the empirical formula that has the smallest whole number ratio of constituent elements, carbon, hydrogen, and oxygen. So we are using concentrated sulfuric acid as a catalyst. Right here, H plus is from concentrated H2SO4. And apparently, there can be an effect of diluting the concentration of sulfuric acid on the yield of the reaction. And that's because dilute sulfuric acid means excess water will be introduced to the equilibrium. And water happens to be a product of, it happens to be one of the products of our equilibrium, meaning that with increase in the product amount, the POE will shift to the reactant side. POE shifts to reactant sides. Therefore, as a result, product amount will be lower than, will decrease, product amount will decrease, reactant amount increase, percentage yield will decrease. Why is ester more volatile than alcohol? The alcohol we had was a primary alcohol that had a hydroxyl group on carbon 4. If we name this molecule A, which is quite difficult but doable, we can first acknowledge how there is an alkene that's defined as but-1ene with hydroxy group on carbon 4. 4-hydroxy-but-1ene has hydrogen bonding where the ester does not, and that's why B is more volatile, stronger intermolecular forces. Stronger intermolecular forces where A has hydrogen bonding and B has only dipole-dipole, and LDF, London dispersion forces. 4-hydroxy-but-1ene is an alkene, therefore is able to electrophilically attack bromine. To have bromine integrated to the molecule and become a bromo alcohol. Electrophilic addition has the physical observation of decolorization, where bromine liquid initially will have orange-brown color that will decolorize, turns colorless as bromine is integrated into the alkene. Decolorization from orangey brown. We have sulfur reacting with oxygen to produce sulfur dioxide, and we are going to find the amount of sulfur dioxide produced when 500 grams of lignite that contains 0.4% of sulfur is used. So let's work out the amount of sulfur, because the amount of sulfur will equal to the amount of sulfur dioxide. The mass of sulfur used is going to equal to 500 grams times 0.004, which is 2 grams. And we're going to divide the mass of sulfur by the relative atomic mass of sulfur, which is 32.02. Sorry, 32.07 grams per mole. Okay, as a result, we will have mole value of 0.062 mole, which is the amount of sulfur dioxide produced as well. Sulfur dioxide may dissolve in water vapors in the atmosphere. To become sulfurous acid. Now, sulfurous acid is a weak acid. It's the sulfuric acid, H2SO4, that is strong. And therefore, H2SO3 produced is not as dangerous. So the dangerous sulfuric acid is produced when sulfur dioxide, before it dissolves in water vapors, reacts with oxygen again. This time with half oxygen to produce SO3, sulfur trioxide. And it's the sulfur trioxide that dissolves in water vapors to produce H2SO4, strong acid. That's dangerous. Sodium thiosulfate reacts with hydrochloric acid. Yes. And we often use crossmark, X crossmark, to determine the end of reaction or the progression of reaction, because the product formed will contain sulfur solid, which precipitates and make the product solution cloudy, invisible, and therefore the X mark invisible. We're going to maintain concentration identical to measure the effect of different temperatures on the rate. Well, we've got temperature, concentration, surface area, and catalyst as the four major factors that affect the rate of reaction. Well, we're investigating temperature, so we're not going to control temperature. Concentration is already controlled. Surface area is not controllable because that only applies to solid state reactants. But we're using sodium thiosulfate and hydrochloric acid that are both aqueous, so we cannot control surface area. Catalyst, we're not using any catalyst, therefore we are not going to control whether different repeats are catalyzed and not catalyzed. So what do we need to control? What else do we need to control? Well, we are basing the rate of reaction on the time taken for the X crossmark to be invisible. Therefore, the visibility factors that affect the visibility of the X mark needs to be controlled, and the first factor is the light intensity of the room. If the room is brighter for the second experiment or fourth experiment, then the visibility will be higher for the second and the fourth experiment. We also need to make sure that the same mark is used. Usually we have a paper with X cross marked, unless we use different X marks, it's not a problem. But if we do, we need to make sure that different marks are written using the same color and thickness. Finally, we need to use the same conical flask. The same conical flask because the volume of our solution will have the same depth only when the shape of the conical flask are identical. And obviously, if we have higher depth of solution, then the visibility of the X mark will be lower. So we want to make sure that same depth of solution is used by using same conical flask for all the experiments. The environmental impact is acid deposition, and to prevent acid deposition from coal there are many ways. Firstly, use less coal. Use minimal coal combustion by using alternative energy, but alternative energy, hopefully renewable. Second, we can recapture sulfur dioxide that is produced before SO2 escapes to the environment, to the atmosphere. And finally, we can not produce sulfur dioxide in the first place if we use pure, cleaner coal without sulfur. How is this possible? Well, we are interested in burning hydrocarbon inside coal, and sulfur is not what we want to burn. It's just that it's an impurity within coal that if we make efforts to remove that before combustion, there will be no SO2 produced in the first place. Any of these three, any two of these three methods would work.